This is a video for me to document creating a better filter for square waves to turn them into sine waves. So in the previous video, I had a LCR bandpass filter measuring the output across the resistor of a LCR circuit. And this achieved a sine wave, but it wasn't very good looking. And then I thought to myself, a square wave is essentially just the odd harmonics plus the fundamental harmonic of the square wave's frequencies. So therefore, if I want to filter out the harmonics higher than the fundamental harmonic, I actually don't need a bandpass filter. The higher harmonics can be totally filtered out by a low-pass filter. So instead of measuring the voltage across the resistor, if both of these elements, the capacitor and inductor, if both of them worked to filter out higher frequencies, I should get a steeper roll-off and therefore create a better sine wave. So that's what I did for this video, which is instead of measuring the voltage across the resistor, I now measure it across the capacitor. Obviously, there's still a lower frequency voltage than the harmonic, but that's the DC voltage, which shifts the square wave to not be centered at zero. However, that's a DC voltage. So therefore, when added to the fundamental frequency, it shouldn't change the shape of the frequency since it just shifts the whole graph upwards. So here's how this second order low pass filter works. When a signal comes in, which is the let's say the higher harmonics, the inductor will stop the higher frequencies from going through. It'll let the low frequencies, but those inductors are basically short circuits for higher frequencies. The resistor acts as a damper, so that around the resonance frequency, it doesn't, it'll decay to a stable voltage rather than having it slosh around the capacitance and inductance and inductor. And then the capacitor shorts out any higher frequencies as well. So higher frequencies, capacitors act as a short circuit, so they'll flow through the capacitor. So therefore, the voltage across the capacitor, which is the voltage basically not shorted, is going to be the lower frequencies only. So this is a second order low pass filter, and the results are on here. So first I'll show you the bandpass filter and what the shape of the output looks like. So as you can see, it's a sine wave, but it's actually not a very good shape because it's way too flat at the top and at the bottom. Sine waves are much sharper than this, and in my higher order low pass filter, with recalculated capacitors and such, this is what I get. So you can see it's much closer to an actual sine wave. However, it is a little bit too sharp at the top, and I'll talk about why. But the shape of it is closer to an actual sine wave. And you'll notice also that it hasn't attenuated the fundamental frequency. For this is a square wave getting generated using the Arduino at 5 volts. And for the bandpass filter, it's only getting about the amplitude times 2 is only about 3 volts, but the second order low pass filter is getting actually 5 volts back out. So that's really interesting because it's more efficient. So next I want to talk about how to actually design the components. So what should L, C, and R be if I want to target a particular square wave frequency. So there's a lot of math in this, and if there's anyone watching that spots a mistake in my deduction and my thinking, please let me know, because I'm not a electrical engineer by trade. A lot of this knowledge is just stuff I learned on my own. So the first thing is to understand how to construct a transfer function, and to do that, there's some prerequisite knowledge. You have to go back to first understand why electrical engineers use the imaginary number to represent phase information. Zach Starr has a really good video on that, so I'm not going to go over that. And then after that, you have to learn what the frequency domain is. And for that, you got to understand Laplace transforms. But essentially, once you finish learning all that, you can basically derive the gain of any circuit by working through its transfer function. So in this case, the second order low pass filter is essentially a voltage divider between the voltage of the capacitor and the series voltages of L, R, and C. So that's going to be the impedance across the capacitor divided by the impedances across L, R, and C, which is given here. So XC over XL plus XC plus R. And that's the transfer function, which is the transfer function indicates the gain of the circuit. So the voltage out over voltage in, essentially. So when I first was deriving this, I was wondering, why do we always set S as JW plus theta? In fact, we don't set the plus theta, we just set as JW. And the reason is because the equations for XCXL are also derived by setting S as JW. That's actually why it's like, for example, why isn't S just anything else? Why is it JW, where J is an imaginary number and W is the frequency of the circuit? And the reason is because we expect sinusoidal steady state. Therefore, there's no theta, because theta indicates decay. But anyway, I'm not going to go further into that, because that's all part of understanding how transfer functions work and how derivations from Laplace transforms work. So basically, once you have this transfer function, you have to simplify it down to this equation. And when you factor out the denominator and the numerator, you get zeros and poles. And Bode's rule, which I'm again not going to try to derive from fundamentals, states that whenever you have a zero, then the gain will increase by 20 dB per decade. And whenever you have a pole, the gain will decrease by 20 dB per decade. So basically, as the frequency increases 10x, your gain will also drop 10x. So here, I use the quadratic formula to solve for the poles S. S1 and S2 is going to be minus R over 2C plus minus the square root of like this term inside here. So from just analyzing this transfer function, we can see that there are two poles. And depending on what R and L, the relationships of R and L, they're either going to be so the real part of this pole is negative, and the imaginary part of this pole either is zero or it's going to exist. And so what does that mean? What happens if we have a pole that has a negative imaginary number and a negative real number and a imaginary number? So I want to show what that actually means. So what that actually means is that if you have a pole with an imaginary component, and let's say your circuit is operating at steady state, and then you just put in a pulse of voltage in the signal source, a pulse like this. if you have a negative real number in the pole, what that means is the circuit will change and then it will decay back to a steady state. So it doesn't increase forever. But if you have a positive real number pole, it's gonna basically grow forever. There is a exponential growth rather than a decay, and this can happen in circuits where there's positive feedback. So like the change gets fed back into the input somehow, and the input again amplifies something. So for example, an op amp where you hook up the output to the positive feedback. However, obviously, this can't be true because otherwise we'll have infinite voltage. And the reason why is because at some point the circuit no longer is represented by the transfer function anymore. In the case of this op amp, it's going to hit the rail supply, the supply rails, and then the transfer function is no longer valid. And then lastly, if you have an imaginary component in the pole, what that means is there's going to be oscillation. So in our case, because we have an LCR circuit, the capacitor and the inductor will slosh the voltages across each other and produce a decaying. The decay is from the real component, but it's going to produce this sort of ripple as you send a pulse through. So that's what this imaginary component means, and so then once we have the pole, we can then go ahead and determine the frequency at which this circuit is going to be rolling off. So if we have this term as an imaginary component, so basically this is negative because the square root of a negative number is going to be negative, then we'll have two poles that overlap basically in the same pole frequency, and I'll talk about what that actually means in a bit. But what happens if this is not negative? So if this is not negative, if it's positive, for example, and we square root this, it's going to produce two real poles, right? Because it's going to be a positive number plus or minus a positive number. And what that actually means is in the response curve, the drop-off will happen at one point, and it'll drop off steeper in another point. But we don't want that, obviously. What we want is we want both drop-offs to happen in the same frequency, so then we can just filter for that frequency, which means that either the square root has to be negative or it has to be 0. So let's take the 0 path first, and then we'll see what happens. So if both poles roll off at minus 20 dB per decade, then two poles in the same roll-off frequency will roll off at 40 dB per decade. So let's solve for the condition where the square root just equals to 0. So you can basically solve it, and then there's a pole at minus there's a pole at minus r over 2l. The pole frequency is the frequency at which it rolls off at minus 20 dB per decade. It's going to be the absolute value of the pole value itself. So I think this is called the corner frequency, my bad. I'm not going to derive why that is, but essentially it's like the pole is a complex number in both the real and complex axis, and the distance of the pole to the origin is the pole frequency, which is the frequency that you have to set your signal in order for it to roll off at minus 40 dB per decade. So then once you solve that, you can obviously solve for the distance by Pythagoras theorem. It comes out to be r over 2l. And therefore the frequency, assuming that this, so therefore the frequency is going to be r over 4 pi l if this this term inside the square root is satisfies this condition, because then it'll be 0. And so, well, we just arbitrarily pick the square root to produce 0. what does this actually mean? So when it's 0, it actually satisfies a condition called critical damping. And so next I want to talk about damping. So essentially what damping is when a oscillation happens, how fast does it take to settle? So for example, a highly damped circuit, the oscillation will happen it'll disappear very quickly. So it'll look like something like this. This is high damping, which means there's a high resistance in the circuit. And a low damping, the oscillation will happen for a long time before it settles down. So this is low damping. So when it's critically damped, what this means is that the damping is sufficient such that it produces, let me just try to find here, it's sufficient that it never jumps over the step voltage. So if we put in a step voltage to the signal, an overdamped response is going to basically have a slower response. An underdamped response is going to overshoot the changing voltage and therefore produce a couple of ripples. And a critically damped circuit basically is the perfect point where it has the fastest possible response, but slower than the underdamped case, but it will never overshoot the change voltage. So that's what this damping means. And by changing whatever is inside this imaginary square root changes the damping factor, essentially. So how does this factor into our filter, right? So what this actually does is when we look at the frequency response, so this is the time domain response that I just showed, but in the frequency response, for a critically damped, so this is basically the gain of the circuit graphed with the frequency that we're passing in. So like if we passed in a frequency of some frequency, how much is it attenuated by the filter? And in this case, if it's overdamped, it's going to look like this kind of roll off here. And then if it's critically damped, it'll have a particular type of roll off. And if it's overdamped, it'll produce a peak in resonance. So you might be wondering why does it produce this peak if it's underdamped? And the reason is because if we come back to here, when it's underdamped, right, the voltages are sloshing against each other, like sloshing against the inductor and the capacitor during resonance, and that's what's causing this sort of voltage peak even above the supply voltage. You can also think of it as, like in the circuit, sorry, just trying to find the circuit again. You can also think of it as, in the circuit, if the resistor is really small, causing the underdamping, there's nothing that's stopping the current from switching between the inductor and the capacitor. So therefore, during resonance, there's current coming from the supply and current sloshing back and forth in the L and C. So when it's high current, it's going to generate a high voltage across the inductor. And therefore also a high voltage against the inductor in the capacitor in the negative direction. So therefore that's what you see in this little peak in the in the Chebyshev filter. So in the critically damped, so we just designed some values for the critical damping. So these two equations make sure that it's critically damped. Now, let's solve this and find, actually no, we don't actually have to solve this because there's actually a better filter than being critically damped, which is the Butterworth filter. So that's what I'm going to explain next. So what happens? No, actually, my bad. I do actually first calculate the values for critical damping. So we want to find a couple of things. So like, let's say we have a critically damped filter. Like we designed it using these parameters, right? What kind of gain are we expecting at the roll-off? So we know that the roll-off is going to be at the pole frequency's roll-off is going to be at minus 40 dB per decade. But at that frequency, what is the gain at that point? Because if it's rolling off at minus 40 dB per decade, but the gain is at, let's say, 0.1, then that means it's already dropped it so much that the filter becomes bad. So let's look at the how we do that. So we basically use the transfer function, and then we plug in the pole frequencies that we solved using the quadratic equation, and we arrive at, there's some algebraic steps, but then eventually we arrive at this equation where the h of s is 1 over LC divided by s plus 1 over root LC all squared. And from here, we apply the critical, so from here, we plug in for h of s, if s was the corner frequency, which we know is which we know is r over 2l because we solved for that earlier. Then we come over here, and then the gain is the absolute value of the transfer function, which using Pythagoras we work out to be a half. So that means that for this particular filter, the gain at the highest roll-off of minus 40 dB per decade is going to be exactly at a half. So this is the Butterworth filter. The cutoff frequency, which is 1 over root 2, happens before that. So therefore, it's actually not that great. Maybe by under-damping it a little bit, by allowing the swishing a little bit, we can actually make the cutoff frequency and the corner frequency a bit closer. And it turns out that the definition of a Butterworth filter is if the two are the same. So if this corner frequency equals to the cutoff frequency, we end up with a Butterworth filter. So here what's happening is the cutoff frequency equals to the roll-off at 40 dB per decade. So therefore, the gain is at 0.707, which is much better than our critical damped filter. Next is, so how do I find the equations which can create a Butterworth filter? So here it is. So when you design a Butterworth filter, there's universal equations that define the Q factor, which is basically how it's another way of writing the damping factor, which is like how responsive is your filter. And these equations for the second order and third order are derived from physics. So it's actually it's like a mathematical relationship between oscillations and damping and all this stuff. So I'm not going to rederive these. But essentially from this, you can prove that the undamped natural frequency is the geometric mean of the pole frequencies. So what this means for us is that because we have two poles, the natural resonance frequency of our LCR circuit is actually just the pole frequency. And this is proved by basically rearranging some of the algebra in here. The next thing we can also prove is that for Butterworth filters, the Q factor is 1 over root 2 for a second order. So here we basically know what the Q factor is, and we know what the transfer function is, and we essentially just match the terms. So this is the original transfer function. We rewrite it in the standard form, and we know the Q factor is 1 over root 2. So therefore, we have to equate R over L, make it equal to root 2 times the undamped natural frequency, which also is the corner frequency. And then you basically do a bunch of algebra on that, and then you arrive at these two equations. So these two equations now define the constraints for the components in your second order low pass LCR filter. So now I go and plug in some numbers. So I have some constraints on my circuit, right? So for example, because I'm using an Arduino outputting 5 volts, I need to make sure that even at resonance, it doesn't produce more than 20 milliamps. So therefore, I have to have a resistor that's higher than 250 ohms. And that's going to constrain my L and C to a simultaneous equation with 2 unknowns. And so working out, if I pick a 220 ohm, which I do have, then L and C needs to be these values. And then as I tweak the 3 numbers, I come up with 2 solutions which seem the best. So for example, the 2 are use a inductor that's 330 microhenries, a resistor that's 330 ohms, and either a 6.8 nanofarad capacitor or a 4.7 nanofarad capacitor. So which one do I use? Because they're both quite close to satisfying these constraints. And the way to pick is that I determined, there's probably better ways, but the way I determined that is I just calculated what the attenuation is at the fundamental harmonic of the square wave and the third harmonic, which is the next harmonic present. And for the 6.8 nanofarad, the first harmonic produced the first harmonic, which is the frequency I want, the sine wave that I want, had an attenuation of 0.55, had a gain, sorry, of 0.55. And then the third harmonic has 0.079. So you can derive this by basically plugging the frequencies and LCR values back into the transfer function. And this is a ratio of 6.962. So compared to a 4.7 nanofarad, which produced a ratio of 6.929. And so therefore, this is actually better. So it's better to use a 6.8 nanofarad. But I decided to still use a 4.7, just because there should be a little bit more resistance than just my resistor. Since what happens is there's parasitic resistances in the circuit, and also there's parasitic capacitances as well in the inductor. So it should push this 4.7 a little bit up, and the ratio is not that different. So I essentially ended up using 4.7 nanofarads for the capacitor, 330 microhenries for the inductor, and 330 ohms. And lastly, I just want to show you some simulations that I made on the computer, that I made in LT Spice. So let me just... Cool. So first of all, I had a look at trying to simulate the actual LCR low pass filter. So as you can see, I have an LCR circuit set up here with a square wave pulse, and I have a transient analysis which measures it at 10 milliseconds after it starts, for a couple of cycles, and it produced this sort of teal curve. As you can see, it's not a perfect sine wave. And at first I had a look at this and it seemed a little bit high. So why is it shooting over 5 volts? Because that makes no sense, because the square wave itself was only 5 volts. And then I realized that what was happening was, even though the square wave is 5 volts, the fundamental harmonic present at 125 kilohertz is actually more than 5 volts. In fact, if you break down a perfect square wave using Fourier series, you'll find that the fundamental harmonic has an amplitude of 4 over pi, which is slightly over 1. And um, yeah, so that's very very strange. But anyway, so by by checking this, it seems like it's actually correct because what I did here is I used a step directive, spice directive, to check how this LCR circuit will just normally respond to a higher harmonic frequency by itself. So not a step wave, but just a sine wave. And here's the result. So there's a fundamental frequency over here. So this is this like big green curve. And then these two harmonics are the third and the fifth harmonic. So this is how the filter filtered out the first, third, and fifth harmonics. So it's attenuated the third and fifth a lot, as you can see. Even though they were originally smaller than the first harmonic, it's attenuated it to be much smaller. And when you add them together, so it creates this sort of blue curve. However, what you'll notice also is that this blue curve is not in phase with the first harmonic, and it's not in phase with the square wave. The reason is because filters introduce reactance. So my capacitor and my inductor has reactances, and it actually causes a phase delay. And the phase delay is different for different frequencies. It shifts the phase delay more and more as the frequency increases. So therefore, it's basically adding the peaks at a later and later time, which shifts this peak to the right. And then lastly, there's also these two simulations. Let me just pull them up. There's a draft 12. Yeah. So I wanted to also show, sorry, just draft 12 and this one as well. Yep. So I also wanted to show how the filter will respond as the resistance changes. So the resistor is damping the circuit, right? And I wanted to see this response as I change the damping factor. So here I have a step directive to change resistances to be 100, which is very underdamped, 330, which is my circuit, and then 1000. And I'm using a AC frequency analysis to step through the different frequencies. And as you can see here with the three graphs, which I've recalculated for gain, for the 100 ohm underdamped case, I actually get a massive spike. The gain goes up all the way to 2.7 at the frequency before the drop off. And so I started wondering, like, is this phenomenon used anywhere? Because I'm not using an active component, and I have achieved amplification. And it turns out that this is called resonance amplification, and it's not very frequently used, but I think there are some applications in like radios and things like that. For my Butterworth filter, I'm getting a gain of slightly above 1 at the resonance frequency. But this is because, I've actually, it's not exactly a Butterworth filter. I've changed the resistances a little bit such that it's under damping compared to a Butterworth filter, slightly. I don't have the exact components needed for that. But yeah, so a Butterworth filter essentially is the maximum amount of, the minimum amount of damping you can have before the gain ever shoots over 1 anywhere in the gain curve, in the gain frequency curve. And then in the underdamping case, you can see that it never goes over 1, but the response is much slower. So the curve is it takes much more frequency for the attenuation to reach a lower value compared to the other two. Yeah, and that's it.